All right. How do you guys feel about this?
Interesting.
Interesting, you said? Okay. Do you get it?
Yes.
Okay. Well, I have a worksheet. I haven't posted it because I was rushing to class, but I'll post it right after class. I have a worksheet to where you have to draw out all the Lewis structures and then you can determine the shape from the Lewis structures you drew. Now, I have one more topic to talk about, which is polarity, but I still need like 20 minutes for it. So you guys want to take a break or you want to keep going? Want to take a break?
Yes.
Okay, let's take a quick break and then we'll come back and I got one more thing to talk about and that'll be it. And everything from then on, everything that I've talked about up to then will be on the test on Thursday. So we can take a 15-minute break. So we'll come back, what time is it? It's 2:08. Come back at 2:20, 2:25.
Okay.
All right, see you guys in a second. Board. We can say it's non-polar if the electrons are shared equally. And an example of electrons being shared equally would be, for instance, if we think about nitrogen gas. Remember, we drew the structure that looks like this. In this bond here, both of the atoms are nitrogen, so their electronegativity is going to be the same. So it's not like any partial negative or partial positive is going to form because they're the same atom. They're not going to pull any different. So they're going to share this bond, share the electrons in this bond equally. Does that make sense to you guys? Basically, if the atoms are the same, we can go ahead and assume that the electronegativity difference is 0 and they're going to share the electrons equally. But if the atoms are different, there's a great possibility that they're not going to share those electrons in that bond equally, and we call those polar bonds. Now, we can have polar bonds and polar molecules, and we can have non-polar bonds and non-polar molecules. I'm just going to jump to it to figure out how you decide if your molecule is polar or non-polar. It's important to know if these molecules are polar or non-polar just because, you know, polar molecules like other polar molecules. Like for instance, you know, with our water is considered polar. It likes to mix with other polar molecules. So it's important for us to know whether our molecule is going to be a polar molecule or non-polar. So the easiest way that I find for you guys to know this, I'm going to give a quick example and then I'm just going to show you my shortcut. So if we look at carbon dioxide, let's go back to carbon dioxide. Carbon dioxide, remember it looks like this. When we look at the central atom of carbon and compare it to the oxygens, carbon and oxygen are two different elements. They have two different electronegativities. And because of that difference in electronegativity, they're gonna form a polar bond. So in this case, oxygen's closer to fluorine. So we're gonna assume that oxygen's more electronegative. So it's gonna have the partial negative on the oxygen, meaning that the bonds, the electrons in this double bond are gonna lean towards the oxygens. So the electrons in these double bonds are gonna lean towards the oxygens, leaving that partial positive on carbon. So we have this dipole moment here, and in this case, what ends up happening is, although these are polar bonds, both of these bonds are polar, it doesn't mean that the entire molecule is polar. So what ends up happening is saying the electrons point this way and the electrons point this way, but overall it's like saying, okay, I'm going -1 and +1, and my -1 and +1 cancel each other out and I'm left with 0. So the electrons in the entire molecule are being shared equally, and we're left with a non-polar molecule. So although carbon dioxide has polar bonds, meaning that the electrons in the bond are not shared equally, the overall molecule ends up being nonpolar, meaning that the electrons in the entire molecule are being shared equally. Amongst the different atoms in the molecule are being shared equally. And this is a tough concept that it's hard for some of us to understand, but what ends up happening is you have to use vector addition to figure out if these bonds cancel each other out or if these bonds are going to add up to have a overall difference in electronegativity. And the vector addition is kind of tough. So I think an easier way to look at this is if we look at our molecular geometry table, we go back to this table. And the way I describe it is I say, all right, we can just draw rows here because this is really what this looks like. It looks like this. Uh-oh. All right, and I'm just gonna make another column here that says polarity. This is my polarity column. And my polarity column says that, all right, if you have a linear molecule, meaning you got two electron groups, bonds, it's just a linear molecule, we can go ahead and say that this is a non-polar molecule. Now, this only works if all of the atoms in this linear molecule, meaning like for carbon dioxide is considered linear because look, we got 1, 2 electron groups are both bonding, 0 lone pairs. It only works that this is going to be a non-polar molecule because both of these end atoms are oxygen. If one end atom is oxygen and the other one is going to be like phosphorus, that's not going to work. They're not going to cancel each other out. They have to be the same end atom. So I also put a star here that says end atoms have to be identical. If they're not identical, we can automatically assume that our molecule is going to be polar. If not, the molecule is polar. Okay, so the example here is carbon dioxide. The end atoms, oxygens, they're both oxygens. We can assume that it's going to be nonpolar. Now, when we get to trigonoplanar, same thing. You can assume it's going to be nonpolar as long as the end atoms are all the same. So let's see, do I have an example of that? I can't think of an example off the top of my head for this one. When we get to this bent, this trigonoplanar bent, we can assume that this is going to be polar even if the end atoms are the same. We can go ahead and assume that it's going to be polar. Anytime you have a bent molecule, the vector addition does not add up to equal 0. So we can say that it's polar, meaning that the electrons in the molecule are not going to be shared equally. So even down here, when we say tetrahedral bent, we can go ahead and assume that it's polar. When we have tetrahedral, it's non-polar. And here we can go ahead and assume that it's going to be polar as well. Basically, when you have these lone pair, the lone pair pull on the central atom in a different way, and it affects the molecule overall, making it polar. Here, let me circle this lone pair too. So we can say there's two things. Anytime you have a lone pair, we can say that it's polar. And as long as the end atoms are identical, we can follow this. If the end atoms are not identical, you cannot follow this scheme. Let me give you an example of what I mean. CH2O. Here's an example. If I draw this out, this is telling me I have a carbon. Remember, we say carbon's always going to go in the middle. In this case, if I have the carbon, what's going to happen is I'm going to draw hydrogens and then an oxygen like this. And when I draw the overall shape, if I do it correctly, it ends up looking like this. 1, 2, 3, 4. Now, this has 1, 2, 3 electron groups, 0 lone pairs. 3 bonding, 0 lone pair. So I'd say 3 electron groups, 3 bonding, 0 lone pair. You're automatically gonna think it's non-polar, but because all of these end atoms are not hydrogen, or they're not all oxygen, they do not cancel each other out in the same way. So this molecule is automatically polar. Does that make sense?
Yes.
Okay, as long as the end atoms are identical, we can say, okay, we can follow the non-polar rule, but because they're not, we gotta assume that it's polar because although this hydrogen and this hydrogen are the same, this oxygen has a different pull on the electrons than the added up hydrogens do, and they do not cancel each other out. All right, so the worksheet that I have to put up on Brightspace looks like this. It's not there yet because I was rushing to class. Looks like this, and it says, basically, what I want you guys to do with this is to draw the Lewis structures, and then after you draw the Lewis structures, I want you to be able to say the geometry, like the molecular geometry, and determine whether or not it's polar or non-polar. Now, when you talk about ions, you don't have to worry about whether an ion is polar or non-polar because an ion has a charge on it, meaning it's either missing or gaining electrons, and they're automatically polar. They're automatically not going to share the electrons equally.
All ions are polar.
Ions.
All are polar.
Uh-huh. All right, so the directions don't say this on the sheet, but what I'd want from you guys is to, I'm going to say it, I'll write it out here, and I'll post it like this. Draw Lewis structure.
It's not on Brightspace, right?
No, not yet. I was just rushing to class and didn't get a chance to put it up. So draw the Lewis structure, and then we're going to determine the electron and molecular geometry. And then we're going to determine if it's polar or non-polar. And so then the third step says determine the polarity. And determining the polarity is basically saying, is this going to be polar or non-polar? And let's just do one together. Water's a good one to do. I know we've drawn the Lewis structure, but let's just go through the steps one more time because water comes up on the test and like on the final a lot. And I just like to go over it multiple times. When we look at water, remember, we're just going to count the valence electrons. 1 for each hydrogen, so that's 2 plus 6, that's 8 valence electrons. We put oxygen in the middle, looks like this. We subtract 4 for each single bond. That means we have 4 left to play with. Those 4 that we have left to play with, I say 1, 2, 3, 4. Now we are out of valence electrons. Remember, hydrogen's happy with 2. If we look around the oxygen, it has 2, 4, 6, 8. Now, when we go, this is the Lewis structure. So this is 1. The second part, I'm saying, determine the electron and the molecular geometry. 1, 2, 3, 4 electron groups around the central atom. 2 are bonds. 2 are lone pair. LP stands for lone pair. In this case, I'm going to say it's tetrahedral bent. The electron geometry is tetrahedral. The molecular geometry is bent. And then because I'm going to follow the table on whether or not it's polar or non-polar, when I go to here, it's 2 and 2. It's 4 electron groups, 2 and 2. That means it's polar because all of my end atoms are hydrogen. These are both hydrogen. So 3 says that it's a polar molecule. Does that make sense, guys?
Yes.
Okay.